And I would like to thank the organizer for putting this nice scientific program together. Not only that, but also the wonderful excursion that we had yesterday. So very much appreciated. So as you see, I will talk about the multi-channel Kondo lattices. And this is a topic that I got interested in back when I was at Rutgers. Oh. Oops, sorry. When I was back in Rutgers, working with Piers Coleman and Ari Vugalter. But then I continued when moving to the University of Cincinnati. So this is my group at University of Cincinnati. And what I will present is mostly the work of my postdoc, Yang Ge. Okay. And I would like to also advertise a postdoc position in my group. All right. So to motivate the problem, let me start with the impurity Kondo model. So most of us are familiar with this problem. If you embed a magnetic impurity in a metal, the spin scattering will fluctuate this impurity, which is very costly. So at low temperatures, the system donates one electron, they form a Kondo singlet, and the system behaves like a local Fermi liquid. Now, things become more interesting when you have multiple channels that compete to screen that impurity. In that case, we model the system with this Hamiltonian. We have 3 electrons. A is a channel index, 1 to K. And then these channels are coupled to the Kondo impurity, to the local moment. And this is an example of what we call a boundary critical phenomena. So the system is critical. If one of the channels is more strongly coupled to the impurity, eventually that channel wins to screen the impurity. Okay, so you can see the channel 1 winner or channel 2 winner, depending on the asymmetry. And if they are perfectly symmetric, the system sits at the criticality. And in this case, we have a residual entropy. So half a log 2, similar to a decoupled Majorana fermion. So a few years ago, we showed that it's possible to isolate this Majorana, and we suggested that perhaps it could be used to do quantum computation. Now, you may think that this is a long way to go to get a Majorana, given that we have lots of non-interacting proposals to realize Majorana fermions. The answer to that is that yes, but if you do a little bit more work to go to 3-channel, you get a Fibonacci anion. So 2-channel is a warm-up, and the goal is to get a Fibonacci anion. Now, it's difficult to realize multi-channel Kondo systems in the experiment. And in fact, this is the list of some of the proposals to realize multi-channel Kondo impurities. So non-Kramer's doublet, if the crystal field in your system is such that you have a degeneracy of 2, or accidental degeneracy or symmetry degeneracy of 2 levels, which is not a Kramer's doublet, that can become like a local moment. And then the 2 spins the 2 spin channels can compete to screen this non-magnetic impurity. The other one is to use a large quantum dot as a separate channel to screen the impurity. This is done by Goldhaber, Gordon et al. Or a version of Kondo impurity, which we call it charge Kondo impurity. There are also proposals based on flow case systems. So applying an alternating AC potential to the source and drain of a quantum dot. And given all the marvelous things that we see in the twisted bilayer graphene, I keep staring at the archival scene, thinking that every day there might be a proposal for a 2-channel Kondo in a twisted bilayer graphene. Now, out of all the systems, only those that are in bold black, they have been realized. Okay, so it's very hard to realize even one, and so it's difficult to make many qubits and then couple them to do anything useful with that. Now, so it's natural to think, would it be possible to somebody goes to the lab, grows a material, and this material already hosts Kondo anyons? So that would be wonderful. So can we have that? Oops. So this requires something we call topological order, or fractional Chern insulator. Right? And this is an example of my wish list, or my what I want to have. I would like to have a lattice of magnetic moments shown in red. and they are coupled to 2 layers or more of conduction electrons that are shown in blue. So in these systems, given that I need perfect symmetry, there will be a continuous channel symmetry present, and this naturally leads to some non-Fermi liquid behavior. An example is this material, praseodymium, iridium, zinc, the family of 1 to 20. In this system has a non-Kramers doublet, and the excited state is a Kramers doublet. So you can see that most of the phase diagram is non-Fermi liquid, and the exponents are what we would expect from a 2-channel Kondo impurity. However, there is a problem, as shown here. If you have this continuous symmetry, which can lead to interesting non-Fermi liquid behavior, the symmetry can be spontaneously broken, right, as shown here. And so the understanding of this non-Fermi liquid behavior is intimately linked with the spontaneous channel symmetry break. So why do I still hope that there would be anything interesting in these systems? Oh, sorry, before going there, I should say that when that happens, when the symmetry spontaneously breaks, effectively the problem becomes the single channel Kondo lattice, right? What do we know about the single channel Kondo lattice? We heard 2 days ago from Jan von Delft that we know a lot. Such a system is described by this Hamiltonian. I have a layer of local moments, a layer of conduction electrons, they are coupled, and the spins talk to each other via the Heisenberg term. Electrons can hop around, and the vertical lines are the Kondo coupling on the last line that couples these 2 layers together. So quite generally, we have these Hamiltonians have at least 2 phases. One phase is the magnetic phase, where I have a decoupled spins form a Fermi surface, and the moments talk to each other, like either magnetically ordered or spin liquid. And there's another phase where the Kondo is dominated, and you have a large Fermi surface. It's a Fermi liquid. And this is proven by Masaki Yoshikawa that this system would have a large Fermi surface. If it has a small Fermi, it can only have a small Fermi surface in the Kondo-dominated regime if it has a topological order. Okay, so why do I still have some hope given this channel, the fact that the channel symmetry can spontaneously break and things could become trivial, is because of this wonderful paper by Nathan Andre and Oriniak from 2000. They look at the 1D 2-channel Kondo lattice, and we have a lot of tools in 1D, like bosonization. They showed that dropping many terms like umklapp, scattering, and so on, they showed that it's possible that Hamiltonian maps to what is shown here. And I can make a, I can visualize this Hamiltonian by what I have, these wires that I have drawn here. So the local moment becomes a right mover and a left mover, and the electrons also become a right mover and a left mover, and the opposite chiralities are coupled together via this last step. Now, because there is a mismatch in what we call Kac-Moody levels of these currents, this opposite chirality wires, they do not completely gap out each other. Okay? Instead, they give rise to, at infrared, give rise to this coset theory. Okay, so it's some exotic theory, which is characterized by its heat capacity. We call center charge. And this is the center charge of this model. For k equal to 1, you can see that indeed it's boring. They will gap out each other. As if you have a single channel Kondo lattice, there's nothing. But k equal to 2, we have a Majorana fermion. K equal to 3, we have a tricritical Ising model, and so on and so forth. Okay, so now we cannot apply bosonization in higher dimension. So instead of that, I use something we call a large N approximation. And in this approximation, I generalize SU2 symmetry of the spins to SUN and represent the spins by abrikoso fermion representation, and then send both N and the size of the spin S to infinity, but keep the ratio constant. Now, that will allow me to write the Hamiltonian in terms of this Lagrangian. So the first term becomes hopping of F electron. This F electron were introduced via this representation, and there will be an emergent gauge field. So it will be a U1 spin liquid coupled to a spin liquid coupled to a U1 gauge field. The electrons remain electrons, but the Kondo effect becomes a hybridization between these C and F electrons. Okay? So this B is a hybridization. Now, the main players in what I'm going to tell you are this F electron which are spin-ons, and those B bosons, which are responsible for hybridization. We may call them holon or slave boson. Now, in the two-channel case or multi-channel case, the complexity comes from the fact that these bosons become a spinor. They are not just a number. And at low temperature, the size of this hybridization is gapped, but the direction is free to rotate, right? And this can lead to non-Fermi liquid physics. Okay, so in the single channel case, the natural things to do is to integrate out fermions. So these are the relevant diagrams, and write down an effective interaction, effective Hamiltonian. You can see that this effective Hamiltonian is a Higgs term, and at low temperature, it likes to lock the external gauge field to the internal F electron gauge field. So this means that the F electron respond coherently to any electric field or magnetic field that is applied, and you have a large Fermi surface. Corresponding to this Higgsing, there is a Meissner effect, which means that if you apply a flux, it cannot terminate in the system. It has to go through the F electron layer. Okay, so now can we do the same thing in the two-channel case? Yes, we can do that. We have done it in this paper, and the effective action is more complicated. You get a nonlinear sigma model, which governs the channel magnetization fluctuations, but you also get this Higgs term. The Higgs term is coupled to that because this omega, I call it disorder potential. This omega is related to the density of skyrmions, channel skyrmions in the system. Okay, so this sigma model has two phases. One phase is a channel ferromagnet when the system orders spontaneously, and a channel paramagnet when the order is broken. And in the channel ordered case, the skyrmions are expelled. So you have a coherent locking between the two A's. But in the other phase, they are proliferated. So the coherent locking is destroyed. You have a small Fermi surface. So all I told you is a non-magnetic transition. The magnetic transition is way to the right. And now, given that I have a small Fermi surface, it's natural to ask, is this a FLS star? Do we have topological order? What happens with the Oshikawa's theorem? Okay, so, but the punchline from here is that this type of mean field plus fluctuation predicts a channel symmetry break. Okay, and this agrees with DMFT. Unfortunately, it does not agree with cluster DMFT, right? This is Inouye and Motoma has done cluster DMFT, and they don't find spontaneous channel symmetry breaking. So what is going on? Do we have channel symmetry breaking, or we don't? And so going back and looking at what we did, it turns out that we were not really allowed to integrate out fermions because we had gapless fermions in the system. I showed you this spinor, and it turns out that no matter where this spinor points, there is always one mode that is gapped, but the other mode is gapless. Okay, so that was not entirely kosher. We need a more sophisticated large N, and this is going to be dynamical large N. I'm going to tell you about. Okay, so within this dynamical large N, we do the same thing as before. The only thing that is different is that we send the number of channels also to infinity. So K goes to infinity, but the ratio of K and N gamma remains fixed. Okay, this was initiated by Parkole and George in 1997. But in a series of papers, Piers and I went back to this problem, and we combined it with Arvos-Arbach description of magnetism to study quantum criticality in heavy fermions. Okay. So how it works is that now the bosons and fermions, they acquire self-energies, right? So you can see that the spinon can come, decay into an electron and a boson, and they propagate and recombine again and so on, or same with the boson. So this leads to a set of self-consistent equations. I'm showing it here. So this is the self-energy of the boson and a F electron. Together with the Dyson equation is a self-consistent set of equations that we need to solve to know about the system. This is similar to the SYK model. Okay, and so the improvement that we did, you see, is that we have introduced this momentum dependence of the self-energy. So we fully capture all the spatial and temporal fluctuations of the self-energy. So let me apply first this method to a one-dimensional two-channel Kondo lattice. or multi-channel Kondo lattice is shown here. And on the left, I'm showing you the spectral function of bosons and F electrons. So as a function of momentum and frequency. And you can see that it is very incoherent, right? The spectrum is everywhere, non-zero everywhere, but it vanishes outside the light cone, as it should. So it turns out that this is a conformally invariant fixed point, and this spectra has a very simple description. So this at low energies, you can just use this conformally invariant ansatz to recover the whole fixed point. And not only that, these critical exponents can be worked out analytically, and they agree very well with the numerical results. So one thing that I would like to emphasize is that such a fixed point can never come from any DMFT calculation, not DMFT and not even its extensions, because it relies strongly on the momentum dependence of the set function. Now, knowing the system, we can, knowing this critical system, we can study its deformations. For example, we can ask what happens if I go to this Kondo lattice and favor one of the channels a little bit more, right? So the result is shown in blue. So you can see that as I cool down the system at low temperatures, the asymmetry between the channels disappears and the symmetry is recovered. So this agrees with the Mermin-Wagner theorem. Right? On the other hand, if I go to infinite dimensions, a slight channel asymmetry is boosted and one channel completely decouples at low temperature. Okay. And so since we know the critical exponents, we can work out this exponents also very easily. So this is induced symmetry breaking. What happens to do we have spontaneous symmetry breaking? For that, we need to go to 2 or 3 dimensions. So this is 2 dimension. We put the system on a honeycomb lattice. And again, I'm showing you the spectrum of F electrons and the bosons along a cut in the Brillouin zone. And again, they are incoherent. They vanish outside the light cone. And there is also a very phase structure for the F electron. This is shows the phase of the F electron, and you can see there is a winding around K and K prime points. So the main message is that the system does not order, right? So it's a symmetry preserving critical point. And it's rather even a conformally invariant fixed point, like a 2+1 conformally invariance, because this whole system can be described by these Green's functions shown here. And the Green's functions are invariant under global conformal transformation. Okay, the exponents are again known, and so we know everything about the system. Now, what happens if we deform it? So one way to deform it is to break the time reversal symmetry. So we use the Haldane method of introducing complex next-nearest neighbor coupling. And what happens is that we get a rich phase diagram. So depending on the ratio of the number of channels to the n, there is 2 phases. One phase we call phase 2 is when both spinons and the holons are gapped. And in the other case, the spinons are gapped, but the holons are gapless. Let me show you what happens at finite temperature to these guys. So at high temperature, like this spinons at high temperature is gapless. As you cool down, there is an emergent gap opening up. And for the holons is opposite. It's gapped at finite temperature, but as you cool down, the gap closes towards 0, and becomes gapless. Now, so this is phase 1, phase 2. There is a finite structure within phase 1, depending again on this axis where you are in this axis. There are 2 behaviors. One is that the population of bosons, as you cool down, goes to 0, and the other case is that the population of bosons is constant. So at low temperature, you have an emergent conservation of boson number. This reflects in channel susceptibility. You can see that depending on where you are in this diagram, at a low gamma, you have divergent channel susceptibility. At a higher gamma, you don't. It saturates. Okay, so this is all the data that I had. This is unbiased calculation, and now I want to add interpretation to it. So as I told you, we have the critical exponent of the system. So we can ask, what is the origin of the gap in various phases in the system? Now, we only apply the Haldane fluxes to the conduction electron. However, via this Kondo flux repulsion, it's natural to expect that the same will will be induced in the F electron layer. Okay, and in phase 2, it turns out that the F bar F, like a mass term, is relevant, and this can easily open a gap in the phase 2. But such a term is irrelevant at gamma less than 2. So what is the origin of the gap in the phase 1? That is the question. Okay, so I should say that in the Haldane model, you get it's essentially a TI. You have an edge state running around, but since this term is relevant and opens a gap, you have a counter propagating edge on the F electron layer running on. So this is a complicated system. You have charge fluctuations, you have spin fluctuations, and channel fluctuations. And one thing I have learned from high-energy physicists is that you can study this by promoting your global symmetries to a gauge symmetry. Okay. In particular, this paper, so Rohana Vijayawardena is my colleague next door. And from this wonderful paper, I have learned that, so this paper studies the confinement, deconfinement fate of gauge theories coupled to Dirac fermions. So if you have an abelian gauge field coupled to many fermions, typically fermions screen the gauge field and the charges are in the deconfined phase. If you have non-abelian gauge field, it's more complicated. It depends what happens to the self-interaction. If the number of flavors, fermion flavors, is more than number of the colors, then the self-interactions are negligible. And this is like a abelian field. Again, it will be deconfining. However, if the number of colors, size of the group is much larger than the number of F electrons, then it becomes a pure Yang mill, which is confining. So what is relevant to us? It basically means that U1 charge is always deconfining, and then spin fluctuations, they are confining for K larger than 2n, and channel fluctuations are deconfining for K less than 2n. So basically we get this plot showing here, all the red is when the spin fluctuations are in the confining phase, and all the blue are when the channel fluctuations are in the confining phase. Okay, so back to what we had. Is basically in this regime, the spin fluctuations are in the confining phase, so you cannot have free fermions that have a spin index. So the gauge field wants to glue this C electron to the F electron and make a boson which carries the channel index. So this is a new particle, and it's very much like how you form a proton out of quarks. And now in these two phases, so one phase, this phi A cannot condense because you cannot have a boson which has channel index. It is in the confining phase, the channel fluctuations, whereas in this phase, it can condense and it will at low temperature. As I said, this formation of this bond set can be easily tracked by looking at this bond set that splits from the non-Fermi liquid and comes to low energies, and eventually at zero temperature will hit zero, and then you get condensation and symmetry break. Sorry, how much time do I have? Okay, very good. Right. So now let me go back to this phase 2, which was an easy phase. The point about this phase is that, yes, we do have counter-propagating edge modes, but the Kondo is still going on. So the Kondo is active and it is marginally relevant. So this is actually nothing but what I introduced in the beginning, which is two chiral edge modes that are coupled to each other via this Andreev-Oriniak phase. They form a coset theory. And we can study the fate of this at large n. And in this limit, there is a central charge or heat capacity. And indeed, this is what shows up in the dynamical large n calculation at the large n. Okay, so back to this phase, we have a dynamical mass generation in phase 1, channel symmetry breaking in phase 1a, and we have a topological order in phase 2. I have used the edge modes to argue for topological order, but this is just a convenience. So of course, same thing is happening in the bulk of the system. Okay, so let me summarize. So I think the main take-home message is that multichannel Kondo lattices provide a route toward realization of non-abelian anyons. but there are some secondary messages. One is that the mean fit theory can be deceiving, especially if you have gapless modes lying around. And if in presence of time reversal symmetry, we have a critical state, symmetry preserving. But if you break the tiers, time reversal symmetry, you get different phases like channel symmetry breaking and topological out. Now, this is what I would like to emphasize. So what I have presented was using a Abrikosov fermion representation of the spin at half filling. But we have checked also Schwinger boson representation. So this result is independent of the spin representation. And second, the filling factor is not important as long as you have a conduction electron which has topology, you have edge states running. The Kondo flux repulsion will mirror this on the F electron. You get a chiral spin liquid, and the two are coupled together at the edge and in the bulk by the Kondo effect. So you will have topological order. And with that, let me thank you for your attention.